Assalamu alaikum. In the previous lecture, we discussed about the selection of the circuit breaker, and by doing that, what we do, what we did, we calculate the simple fault MV at any point, and that fault MV should be equal to the fault MV of a circuit breaker. But sometimes the system is so designed when we calculate the fault MV, we don't have the availability of the circuit breaker which met the same fault MV. So otherwise we can say that we have the circuit breakers whose fault MVA is less as compared to the calculated one. So in that case will be using the reactors. As we know that the circuit breaker MVA is given by the base MVA divided by the Thevenin impedance. So base MVA is it is. So in that case when we use the reactor or uh, when we have the fault MVA which is greater than uh, the fault MVA of the available circuit breaker, we can increase the Thevenin impedance in that case so as to meet the actual value of the available fault MV of the circuit breaker. So before going into that, let us see what is the advantage of the using of reactor. So advantage is that efficiency, the first one, efficiency is not affected. So by using a reactor, since there is no power loss, so efficiency will be unaffected. So it reduces the fault current. Since it reduces the fault current, fault MV automatically required will be less. So decrease the short circuit KVA requirement of the circuit breaker. That is the actual use. Disadvantage is actually uh, the actual use. Why we use this reactors in the circuit, just to decrease short circuit KVA requirement or MVA requirement of the circuit breaker. Protects the circuit breaker for inadequate rating. So it also protects the circuit breaker from inadequate rating, or we can say it does not allow the circuit breaker to overload. The amount of current that may overload the circuit breaker, that is decreased by use of these reactors. So the reactors are classified on the basis of their locations. So there are usually three main types of these reactors. One is the generator reactor, another is the feeder reactor, another is the bus bar reactor or tie bus system reactor. You can see the generator reactor is connected between bus and the generator direct. So this type of reactor which is connected between generator and the bus, that are known as generator reactors. So feeder reactor are those type of reactors which are connected between bus and the feeder. So initial point of the feeder and the bus. So such type of reactors are known as feeder reactors. So this is the bus bar reactor. In this case, the reactors are connected between different bus bars. This is one bus bar, this is another bus bar, this is another bus bar. We may have another reactor that is connected between this bus and this bus, like this. So in that case, this becomes a ring bus system. So this is the bus bar reactor, where the reactor is connected between different bus sections. Tie bus system. It is connected between two different sections of the bus. You can see it here. We have a bus, and at this bus we have the load or feeder, and this bus and this bus is connected through a it's the common bus. The common bus and its own bus is connected through a reactor. Such type of reactor are known as tie bus reactors. And the last one is the ring main system. The ring main system, the last three, that is this bus bar reactor, tie bus system, or ring main system. These are actually the different combinations of the this bus bar reactors. These are bus bar reactors because this is the bus and this is also bus. The reactor between two buses are connected. This is the individual feeders of the bus, like this or like this. I have told you that if we use a reactor over here between these two, this also becomes a ring bus system. So these are the different uh, types of reactors based on their location where we use them. So the primary motive of using them is to decrease the fault MVA required at any point. So this further explaining them is best by a simple numerical. I will explain the use of this by simple numerical, and then after this numerical we'll go for the design of this reactor. A small generating station has been divided into three sections. Each section is connected to a tie bus bar with a reactor each rated at 5 MVA 0.1 per unit reactance, a generator of 8 MVA and 0.15 per unit reactance is connected to each section of the bus bar. Determine the short circuit capacity of the breaker with and without the reactor if the three-phase fault takes place on one of the sections of the bus bar. Since this is this type of system, it is this type of a system which is given in the question. So it's the type bus bar. So with the reactor is given reactance is given 0.1 per unit at this MVA base, and we have three generators whose MVA rating is 8 and reactance is 0.15 per unit. So I have drawn this actual system like this. This is generator 1, generator 2, generator 3. This is the part of question which we may require in this solution. So this is the reactor whose value is given 0.1 at 5 MVA. So generator are rated at 8 MVA and 0.15 per unit. First, let us assume that we don't have any reactor. You can see that we might have a short circuit over here, short circuit over here, and short circuit over here. So its equivalent circuit will be like this, because having a bus and then another bus connected to each other will be simply, we can say that its equivalent circuit will be as if this generator is directly connected to this point. Similarly, this generator is directly connected to this point, this generator is directly connected to this point without when we don't have a reactor. So in that case the circuit looks like this, and we are given that determine the short circuit if a three-phase fault occurs one of the sections. Either the fault occurs at this point, or this point. That means without the reactance used, the fault at this point and this point, or this point and this point, or this point and this point will be similar. So that's why I have shown it over here. It can be shown anywhere at this point that is equivalent. That is one and the same thing electrically. So I draw the equivalent circuit. It is the voltage source behind its reactance, that is 0.15, 0.15, 0.5, 1.0 per unit, 150 per unit, 1.0 per unit. So this is the fault point, that is this F, and this will be the neutral. Between this point and this point we have to calculate the XTH. You can see that XTH between this point and this point will be the parallel combination of these three. So parallel combination of these three comes out to be 0.15 divided by 3, that is J 0.05. So the short circuit MVA S is SB divided by XTH. It comes out to be 8 divided by 0.05. That comes out to be 160 MVA. So because the base MVA for generator is 8 MVA. Now let us look for this system when we are using a reactor, and we will find out how this will decrease. So this is the system, type of system, in which we are assuming the fault is at this point. Even if fault is at this point and this point, this will be equivalent electrically. So I will assume that the fault is at this point, and this is it is equivalent circuit. This is the equivalent circuit of generator G1, equivalent circuit of generator G2, equivalent circuit of generator G3. So the reactance is given to be 0.1 at 5 MVA. So we have to calculate it at 8 MVA because we are using this base, that is 8 MVA. So it will be equal to 0.1 into 8 divided by 5. It comes out to be 0.16 per unit. And I haven't written over here, but since it is written and you can check it, it will be equal to 0.16 per unit. So its equivalent circuit becomes like this: 0.15, 0.16, 0.15, 0.16, 0.15, 0.16. You can see these two are in series, these two are in series. So by simplifying these two, it will be equal to 0.31 and 0.31, these two, and the circuit will be like this. These two will then be parallel to each other. So the parallel combination of these two will be the 0.31 divided by 2, that is 0.155. After this circuit, we'll be having these two reactants will be in series. So after adding these two, it will be equal to 0.315. The last one, these two will be in parallel. It comes out to be 0.1016 per unit. So the short circuit MVA will be SP divided by XTA, that is 8 divided by 0.1016, that is 78.73 MVA. You can see it by using a reactance of 0.16 per unit at 8 MVA base. We have decreased it to 160 to 78.73 MVA, almost half of the value. So by using this, you can see that we can decrease the value of a short circuit MV. Let's try to do one design problem in which we'll calculate the value of the reactance of the reactor. So I hope you understood this. The fault point is F and N, and between these F and N we have to calculate the XT. That's why I have drawn it like this. So let's come to the next problem. The problem reads like this: a station operating at 33 kV is divided into section A and B. Section A consists of a generator 15 MVA, each having a reactance of 15%, and section B is fed from a grid through a 75 MVA transformer having a reactance of 8%. The circuit breaker have each a rupturing capacity of 750 MVA. Determine the reactance of the reactor to be present to prevent the breakers being overloaded if a symmetrical short circuit occurs at the outgoing feeder connected to A. We have two sections, you can see. Section A, this is the section A from here to here, and this is the section B. And they are connected to each other through XR, that is the reactor. This section B connects to the section A through reactance A and the transformer 75 MVA to the grid, main grid. So the equivalent circuit of this system may be shown like this. So the generator, behind it is reactance, this generator, reactance, it's reactance, this generator, this is equivalent circuit. So definitely this will be the neutral of this, because the generator will be connected, its positive will be connected to the load and negative will be connected to the neutral. That is negative usually here is shown upwards. So this is the reactance of this is the reactance of the transformer, and since it is grid is shown, it is actually a big grid and its reactance is not given. When big grid is shown, its reactance is not given, its reactance is taken to be equal to 0. That's why I have shown here only 1.0 per unit voltage of the grid without the reactance. This reactance is of course the reactance of the transformer. Let us take this MVA, 75 MVA is the base MVA. So XG, that is the reactance of the generator, will change now because it is given to be 15% on 15 MVA on 75%. It has to be changed. It will be 0.15 into 75 by 5. Sorry, it should be 15 over here. So it comes out to be 0.75 per unit. So I have written here 0.75, 0.75 and 0.75. So its value is given it, the value of the transformer reactance is given to be 8% on 75 MVA. So it will not change, it will be as it is. So it is given now to find the short circuit MVA if the fault occurs on the outgoing feeder of the outgoing feeder connected to A. That is at this point. This is the outgoing feeder. If the fault occurs at this point, we need to calculate the fault MVA. So the fault point is located, that is this. So when we have to calculate XTH, it is calculated between this F and this N. So XTH will be between these two. So it will be, you can see it, these three will be parallel and these two will be in series, and the combination of these two will then be equal to parallel. You can see these two, when parallel combination of these two will be equal to 0.75 divided by 3, that is 0.25, and a series combination of these two will be XR plus 0.08. So the total combination of these three will be, that's XTH will be XR plus 0.08 into 0.25 divided by XR plus 0.08 plus 0.25, that is 0.33. So now, so I have written it again, this XTH is equal to XR plus 0.08 into 0.25 divided by XR plus 0.33. Given that the value of the circuit breaker, short circuit MVA of the circuit breaker is given to be 750 MVA. It should not go beyond the 750 MVA. So it means S is given to be equal to 750 MVA. And SB, that's the base MVA that we have calculated for the different impedances, we have taken it to be 775 MVA. So we know that S is equal to SB divided by XTH, or from this equation XTH is equal to SB divided by S. SB is given to be 75 and S is 750, it comes out to be 0.1. So by using the value of this XTH, this will be equal to XR plus 0.08 into 0.25 divided by XR plus 0.33. It comes out to be equal to 0.1 because it is this. So by simply multiplying this to this and this to this, it comes out to be XR into 0.25. the multiplication of these two will be equal to 0.02. So this is a simple multiplication. It will be equal to 0.1 into XR plus 0.033. So 0.25R XR multiplied by 0.1 XR, it comes out to be 0.15 XR. So 0.033 multiplied by 0.02, it comes out to be 0.013. So XR will be equal to 0.013 divided by 0.15. It comes out to be 0.086 per unit. So this is the value of the XR in per unit. In actual value, we will multiply its base value of the impedance. Base value will be 33 square by 75 because MVA base is 75 and kV base as it is given as 33 kV. So when we multiply this, it comes out to be 1.2584 ohms. So I hope you have understood